As we learn more and more about the structure of electrons in the electron cloud, we should also be learning more and more about how we predict how atoms work, how they do things, how they will eventually bond and do chemical reactions and all kinds of interesting things like that. So, because the electrons dictate a lot of the fun stuff that atoms do, and because the periodic table follows kind of an order, a pattern of how the electrons fill certain orbitals, like how we have the s block and the p block, how we have different energy levels being filled through different rows, and how we fill parts of the s, p, or d, or f block as we go through different columns with the same number of valence electrons in each column, we should get some very similar properties up and down a column. We should get some interesting trends across and things like that. So the periodic table actually lends itself to being able to predict a lot of different trends, a lot of different properties within a row or a column, or looking at changing both at the same time. We just have to pay attention to where on the periodic table things are at and know some extremes of kind of one corner of the periodic table or another. So we're going to be looking at a total of 4 periodic trends. These are not the only periodic trends you can come across, but they're kind of the big 4 that we will be most concerned with in chemistry at this point and further on down the line. The first one, and one of the most fundamental ones, is atomic radius. And essentially, this is how big your atom is. You could think of it as if your electron cloud is kind of the farthest out that your atom reaches, and say your nucleus is right here, then you might think of your radius as how far out you go from the center. Now, technically, that gets real hard to figure out, since the electron cloud is not some strict boundary or barrier that the electrons can't pass. It's a little more difficult to figure out where the atom actually stops. So the more common way we do this, we figure out how big an atom is, or what the radius is out from the nucleus, is we have 2 atoms stick together. And that essentially looks like 2 atoms overlapping their electron clouds. This is a kind of bond. We'll get into that later. It is hard to figure out where the electron cloud stops, but it's really easy to find a nucleus, because it's this big, massive, dense thing in the center of the atom that will really respond to things hitting it, unlike kind of a lot of the empty space of the electron cloud. So if we can, boom, hit one nucleus, and boom, hit another nucleus, and find out there's nothing really in between except electrons, and measure the distance between those nuclei, take half of that, what we end up with is the radius. Okay, so maybe you think, oh, it's a little bit short for being a radius, because it's kind of halfway into another electron cloud, and that's kind of fair. But it's a pretty good measurement compared to just kind of being like, oh, it goes up this far, and I'm going to guess, and stuff like that. So sometimes a better way of putting this is not atomic radius, but covalent radius. Valent being talking about the valence electrons, kind of the farthest out electrons. Co being about cooperating or together with another atom. So looking at the valence electrons of atoms together, shared in a space, and then seeing the radius out from the nucleus through kind of to that point, to that bond in between. So you might see this kind of as you go through a textbook or online. Covalent radius is basically just another way of kind of saying or measuring your radius of an atom. But that aside, we should probably talk about, what this means for us. Okay, so the atomic radius is, half the distance between 2 nuclei. Again, it's how we kind of usually measure it. That's where we get this from. Okay, because it is a distance, we measure it just like any other length, but we use a prefix for something very, very small. Okay, so pico is our prefix here. Just like millimeters or centimeters, it's just a modifier for our unit. So in this case, a pico, something like picometer, is 10 to the negative 12th. So very, very, very tiny, very, very small fraction of a meter. Sometimes you'll also see angstroms, which I'm pretty sure is named after a person. So it's not attached as a prefix or anything like that. It's just, a measure of distance kind of on its own, but it does mean something in meters. It is 10 to the negative 10th meters. Okay, basically what we're getting at is very, very, very small distances. Okay, to give you kind of an idea of, what sizes we're talking about, oxygen in the top right of the periodic table, or pretty close to it, has an atomic radius of about 60 picometers. Okay, so small unit, but a number that we can think about as a result. 60 is an easy number to kind of imagine. Francium, on the other hand, is down in the lower left and has an atomic radius of about 260 picometers. Okay, so francium is about, well, a little more than 4 times the size of oxygen going out from the center. Okay, now as we move from left to right or up and down on the periodic table, we should see atoms get bigger or smaller in a pretty predictable trend, which is why we call it a periodic trend. It's a trend on the periodic table. And what we find with atomic radius in between these kind of extremes in the upper right and the lower left is that atomic radius increases as we move down and left on the periodic table. Okay, so as we move towards that bottom left corner, our atomic radius increases. It gets bigger and bigger. In other words, we're getting bigger and bigger atoms as we move towards that bottom left corner. As a result, if we move up and right, we're getting smaller and smaller atoms. But why? Why do we get this trend? How can we predict that if you are down lower on the periodic table or farther left, you're dealing with a bigger atom? We'll tackle down first. As we go farther down the periodic table, each row is kind of representing an energy level. Like the first row represents the first energy level, second row shows the second energy level, all the way down to 7. So if we are moving down from, first energy level to second to third to fourth, our electron cloud is reaching out farther and farther. Our valence electrons sit farther out from the nucleus in, say, the fourth energy level than they do the third energy level. Now, as we fill up the electron cloud, kind of as we do like the 1s2, 2s2, 2p6 stuff, sometimes we go back inside the electron cloud into the core electrons, like how we go from like 4s to 3d, but still we get this general trend of the farther down in the periodic table you are, the farther out your electron cloud reaches. Since we're talking about how big the atom is based on the electron cloud, the farther down you go, the bigger your atom gets. Okay, so this is our nucleus here. And you had, this is like your first energy level, and then your second, and then your third, and then your fourth, and you keep going and going and going. The distance out from the center is obviously going to get greater and greater as you keep filling up farther and farther out into farther energy levels. So that one's pretty self-explanatory. That one hopefully makes some good sense. But why left? Why do atoms get bigger as we go farther left on the periodic table? Why do elements have this difference? Well, if we are in the same row on the periodic table, then we're dealing with stuff that is all pretty much out to the same energy level. So if we think of like the second row, how we have like lithium and beryllium, we have a big gap. And then we have, let's see, boron. Boron is 5, carbon is 6, nitrogen is 7, oxygen is 8, fluorine is 9, and then neon is 10. Okay, so if all of these are in row 2, they all go out to the second energy level. I'm going to say second EL. Second EL, because I don't really have enough space. So all these are going out to the second energy level. So whether we're dealing with lithium or boron or nitrogen, they have different numbers of electrons, but the distance out they go in the electron cloud is pretty much the same. Okay, they all go out only to the second energy level. It's not like adding in one more electron from carbon to nitrogen makes it that much farther out. It's pretty much still in the same spot. What does change, though, as we go across from here to here, is we start increasing atomic number. So Lithium has an atomic number of 3. Beryllium has an atomic number of 4. Boron is 5. Carbon is 6. Nitrogen is 7. Oxygen is 8. Fluorine is 9. Neon is 10. And that, of course, is counting the number of protons. Okay, protons are positively charged. Electrons are negatively charged, so they attract each other. And this is going to bring up something that is important through basically all these periodic trends. Okay, this attraction between the protons and the electrons determines how big the atom is. If you've got more protons to attract those electrons, they're going to pull in harder. They're going to have a stronger attraction to those electrons. So you can think of it like tightening the belt around the atom. It's kind of shrinking the electron cloud, like really pulling hard and pulling the electrons in closer to the nucleus. Okay, all the while, if we keep increasing the number of protons going right, we're not really increasing how far out the electrons go. So from beryllium to boron, the electrons go out to about the same distance, out to about the second energy level. But having more protons attracts it and brings it in a little bit closer to the nucleus. Okay, so get rid of these. So our atomic radius ends up being biggest on the left side of the periodic table, where we're down to a certain energy level, but we have the least number of protons for that row, for that energy level. Therefore, we have kind of the loosest grip on those electrons in the electron cloud. The farther right we go, the smaller the atom gets because we continue to pull the electrons in closer to the nucleus and not let them go so far out. So with those together, we have the atomic radius also becoming larger. We get a wider atom, something with a bigger radius, out farther left on the periodic table. And stuff gets smaller on the right side. Okay, this is just kind of a little diagram for our attraction. So the more charge you have, the stronger attraction you have also. So if this is not just, one positively charged particle, but a whole bunch, then that is going to increase the force here and here. Okay. So that's something to keep in mind. And distance also matters too. We'll kind of get into that later. Remember that most of what's going to determine all this stuff has to do just with the charge of the protons and the electrons. Okay, so more charge means stronger attraction. That's a big piece, and we'll come back to the other one in a bit. So that's atomic radius. Biggest atoms are down on the bottom left on the periodic table. Smallest atoms are up in the top right. Ionization energy is the other periodic trend we're going to talk about in this video. Okay, ions are just charged atoms. Okay, so the ionization energy is how much energy it takes to make an ion. Okay, now specifically, we want to pick whether it's going to be positive or negative because ions can be either. You could have a positively charged cation because they're positive. Okay, or you could have a negatively charged anion. That's a negative ion. All right, in this case, we're going to talk about specifically making cations. Okay, so how much energy does it take to remove electrons from an atom? Okay, we start with the valence electrons on the farthest out reaches of the atom. Okay, and therefore, how hard is it basically to make a cation out of an atom? All right, we measure this as energy per amount of a chemical. So energy is measured in joules, which is this right here. This is a big J right here. It's a lot of energy, so we measure it with the prefix of kilo typically. So kJ is just kilojoules, and this per mole is just an amount of a chemical that we will deal with more later. So you can kind of ignore that for now. What matters is we're measuring energy. How much energy does it take to take an electron away from something, to have it kick that electron out totally? Okay. To give us kind of a baseline, cesium, down the bottom left of the periodic table, has an ionization energy of 400 kilojoules per mole. whereas helium in the top right has an ionization energy of 2,372 kilojoules per mole. So helium's ionization energy is almost 6 times as much as cesium's, which means it would take about 6 times as much energy to rip an electron away from helium compared to cesium, which might seem kind of backwards at first. We just talked about atomic radius, and we said that the biggest atoms are down the bottom left. So if you have kind of a correlation in your head of, bigger, means stronger or something like that, then you'd think, okay, cesium is a really big atom, and therefore it's going to just be real beefy and really hold on to its electrons or something like that. And then this helium atom is a real shrimp up in the top right that for some reason is just not going to give up its electrons, so much more. So what's going on here? Why does ionization energy increase as we move up and right on the periodic table? Okay, where it gets harder to remove an electron. Harder to remove. Do a little E negative for electron. Okay, well, the first one has to do with how our electron cloud is set up. Okay, so if we are worried about trying to steal away an electron from an atom, we're dealing with the valence electrons. So if I'm dealing with an atom, got our nucleus here, and we've got our energy levels. Okay, I might have electrons inside here, or whatever, but I'm only worried about taking the ones farthest out here. Okay, I want to pull those out. Okay, well, this electron farthest out is going to have an attraction to the nucleus, but it's also being repelled by all these other electrons. So if I've got other electrons in the electron cloud as negatively charged particles, they're going to push away from this electron. Okay, I've actually got a diagram down here that I'm going to use that maybe shows this a little better right here. Okay, and right here too, same kind of idea, but I like this one over on the right. So these outer electrons that we're trying to get to kind of move out, okay, are attracted to the nucleus, but these other electrons inside, we call those core electrons, are going to push out. They're going to repel other electrons. So electrons closer into the nucleus are going to repel the ones that are farther out, which means we have some help getting this done here, getting this to push out the atom, to kick out our valence electrons. So inner electrons, core electrons, actually kind of help to move valence electrons out, to kind of give them a push already in the direction that we're kind of trying to rip the electron. So if we have more inside electrons in the electron cloud, more core electrons, it's like the attraction to the nucleus is less. Effectively, it's like it's not pulling as much. Okay, and that's kind of what's going on here. We have electrons kind of in between the electron we're trying to remove and the nucleus that's attracted to it. So the electrons on the inside that are kind of repelling kind of essentially cancel the effect of the nucleus attracting to the electron, because as the nucleus pulls it in, those other electrons are pushing it out. So it's a little bit easier to tear that electron away. All right. So if we are up on the periodic table, we're dealing with atoms that are small, that don't have a lot of electrons. Okay. Also kind of follows the atomic radius. So if we have atoms that don't have as many electrons, period, and don't go out to as many energy levels, stuff in maybe the first column of the periodic table or the second column, not like the sixth or seventh. Being higher up on the periodic table means we don't have inner core electrons to shield the valence electrons from that attraction from the nucleus. All right, so as a result, it's a little bit easier to kick those electrons out. On the other hand, if you go down the periodic table, you have more and more electrons on the inside of the atom that are pushing those valence electrons in the opposite direction of the nucleus. So if we're trying to kick that valence electron out, we really don't need to put in a lot of energy to pull it off of that atom. Okay, so we end up with a higher ionization energy up higher on the periodic table because our small atoms, something like this, has way less shielding and basically is just drawn into the nucleus. So if I'm trying to remove this electron, I've really got to pull hard on this to try and remove it because there's nothing else on my side trying to push it out that direction. Okay, so highest ionization energy means I've got a large value of energy I've got to put in to be able to remove an electron from something. Okay, and again, that happens up high on the periodic table. Why right? Why right? Well, when we talked about making ions, we talked about atoms that are kind of looking to gain electrons or lose electrons to reach an octet, okay, typically. In more general terms, we're looking for something to get a configuration of electrons that's similar to a noble gas, like something in column 18. Those tend to be very stable, so we're looking for a way to mimic that stable electron configuration. Okay, now elements farther to the left on the periodic table are looking to lose electrons. Okay, so on the left side, we really don't need to put in a whole lot of energy to coax an atom into losing an electron because it's like, ooh, that's what I want to do anyway. I want to get rid of an electron, and chucks it out. On the other hand, on the right side of the periodic table, we have things trying to gain electrons. Things with 6 or 7 valence electrons that are so close to having 8, that kind of magic number, that octet. So trying to give energy to remove those electrons is going to be tough. It's like, man, I just want like 1 or 2 more electrons, and now you're trying to take them away from me. Like, that's the other direction. That's the wrong way. I need more electrons, not less. So we'd have to really, really, really bribe an atom with a lot of energy in order to kick an electron out of one of those atoms. So on the right side of the periodic table, we have to put in a lot more energy to remove an electron, since those elements are looking to gain electrons, not lose them. Okay, so we have higher ionization energies on the right side of the periodic table. Okay. Now, as we get further into this, you can also start connecting some of these periodic trends together. So, we talked about atomic radius. You might also kind of throw in that the smaller an atom is, like in the top right of the periodic table, the stronger the attraction is to those valence electrons just by distance. Those electrons are going to be closer to the nucleus, so they're going to be attracted stronger. If we're dealing with a bigger atom, like down in the bottom left, those electrons are farther and farther out from the nucleus. So the attraction is going to be less, even aside from that shielding effect from the core electrons. Farther distance in between charged particles means less of an attraction. The closer they are, the stronger the attraction. So this is not the only way you can think of these periodic trains and get them kind of explained, but it is kind of a way or two that might help. To summarize these trends, atomic radius ends up being biggest down in the bottom left of the periodic table. So these are our biggest atoms, whereas our smallest atoms are up in the top right corner. Okay, because we're kind of maximizing how many energy levels we reach out to going down. We also minimize how many protons there are in that energy level on the left side of the periodic table. For ionization energy, we have our largest ionization energy values in the top right because we are over on the right side where we've got things that want to gain electrons, not lose electrons, so they're going to hold on tight. Okay, we also have stuff near the top of the periodic table that doesn't have a lot of shielding from the core electrons because there aren't a lot of electrons to shield those valence electrons from those attractions of the nucleus.